Greetings. In today's lecture, we'll be discussing about analysis of redundant frames. To understand the concept, let us begin with the discussion on statically indeterminate structures. Statically indeterminate structures are those structures which cannot be analyzed fully with a reference to available conditions of equilibrium. Means they are having the forces more than the usable available equilibrium conditions. Examples of statically indeterminate structure are continuous beam, 2-inch arches, and trusses. In case of continuous beam, we have n number of supporting span developing n number of reactions which can't be analyzed with reference to available static equilibrium in conditions with a reference to the geometry as well as loading condition. Thereby, there will be unknown forces remain which we have to analyze with the help of developing additional equation either in terms of compatibility or with reference to constitutive relationships. This will define the degree the indeterminacy it will have. It depends upon the number of force which are unknown in it. It goes on increasing as the number of unknown force is going to increase, and this structure to be analyzed, what we will do here, we'll make it as a statically admissible structure by removing one of the forces or the unknowns which are leading to this indeterminacy. The method of removing that forces and analyzing it, we call it as a redundance. Means we are going to remove it the unknown forces. Then we'll suitably utilize the superposition theorem, virtual work theorem, Bettis equation, or Castigliano first principle, Castigliano second principle, and based on that we are going to find out unknown forces by a constructive relationship or constitutive relation. Similar way, in case of arches, the two hinge support at the ends is going to develop unknown reactive forces which are in excess of the available equilibrium equation for that particular structure, hence making it as a indeterminate. Similar fashion, the trusses may be indeterminate or determinate depending upon the number of member forces in excess and number of the end reactive forces in excess, and this will define the degree of determinacy of that particular structure. Now, before going towards the analysis, let's try to have a comparative comparison between statically determined structure and statically indeterminate structure. The tabular format shows some key points of comparison. The very first point says that the conditions of equilibrium are sufficient to fully analyze the structure. Vice versa, we can see in case of statical indeterminate, the condition of equilibriums are not able to fully analyze the structure and to find out the unknown forces. The second point says about the bending moment at any section or the member force in any member is independent on the material of the components of the structure. But in case of your statically indeterminate structure, we are going to use the material properties to find out the constructive relationship so as to find out the unknown forces, like we have done in case of strain energy concept, where we have used material constants like axial rigidity, modulus of rigidity, and many more, where we have the material constant like E, elastic modulus, in the equation to solve the unknown forces. In similar fashion, the bending moment at the section or the force in any member is independent on the cross-sectional areas of the component, but in case of statically indeterminate structure, we are going to use the cross-sectional properties also to find out the unknown forces developed in that member. Like in case of your flexural stresses, we use integration 0 to L m square ds upon EI, which is the equation related to strain energy stored by a structure under flexural loading, where EI stands for modulus of rigidity, and here I depends on the cross-sectional area of that particular member. In case of determinate structure, we in one of my lecture I said that it is free from the stresses developed by the temperature changes or the stresses developed by the lack of fit. What's the meaning of this? The structure is so flexible that it's going to have negligible effect of the temperature rise or extension of the member due to temperature rise. They are going to compensate, or the stresses which has been developed due to lack of fit. What's the meaning of the lack of fit here? The member is either too long or the member is either too short. This is deficiency which has been developed due to structural your fabrication work or the human error while having the cutting length of that particular member. So the structure is flexible enough. If it is too short, it will get deform and adjust. If it is too long, it will get elongate and adjust. But this thing will not happen in case of your statically indeterminate structure, because in case of statically indeterminate structure, nearly the degrees of freedoms are going to locked, and in the locked degrees of freedom, the member will be subjected to either compression or tension due to increase in temperature or due to stretch or pull applied to have proper fitting in case of too short member, or in case of too long member, the member will be subjected to additional compressive forces. Thereby will be additional forces develop in the member, and we have to address these additional forces in access to the member forces, and we have to give due consideration while designing the cross sectional areas for the material depending upon what type of the secondary stresses are arise due to temperature change or lack of fit. Now we'll move towards the part how to analyze it. So we will use the Castigliano's second theorem to analyze indeterminate structure, which states that in any and every case of statically indetermination wherein an indefinite number of different values of the redundant forces satisfy the condition of statically equilibrium, their actual values are given by those that render the total energy stored to a minimum. Means what he wants to say, the number of unknown forces which we want to find out, we can find it by with the help of minimizing the energy stored by the body under the action of that redundant force. Let us explain this, let us get this concept with certain explanation. For that, let's continue, we move with a continuous beam. In case of the continuous beam, there are three supports. Okay, it is two span continuous beam. There are three supports leading to the three reactive forces, development of three reactive forces under the given loading system. If you see the force system here, force system is a coplanar parallel force system, and the usable equilibrium equation for this coplanar force system is only 2. Means summation of forces in x direction and summation of moment at any point will be equals to 0. If I use these two equations, it's not possible for me to find out the three reactive forces RA, RB, and read this as a RC here. So what I will do, I will select one of the force as a removable force. So what I will do, I will make the structure as a statical admissible first, and then I will analyze it. Now what I will do, I will remove this one and I will say it as a redundant force. I am removing it. It is said to be excess in excess. So which are where we can say this redundant force be x, so that this will become statically admissible, and once it becomes statically admissible, now I can find out the unknown reaction RA, RB, and RC. Now to know the value of RA, we will utilize the Castigliano first theorem, which states that the deflection caused by a force can be found out by taking the partial derivative of total energy stored by the system with reference to the force under which we want a displacement. So this was the first theorem, which is stated by Castigliano, dou ur upon dou x equals to 0. Now what we require, what is the maximum value of x? It may vary from 0 to n number, but I want a maximum value. So what I will do, I will have the minimization or maximization of this particular deflection which is being caused by the unknown force. Means I am going to minimize the strain energy value with reference to the redundant force. For that, what I will do, let's take a concept related to here fluxural member. So here in case of this continuous beam, it's a fluxural member. We know strain energy is given as summation of integration 0 to L m square ds upon 2 EI. So what I will try to do, I will try to minimize this strain energy with reference to the Castigliano statement. So what I will do here, first I will find out the deflection caused by this reactive force. It will be dou ui upon dou x, partial derivative of strain energy stored by the system with reference to the force under reference. So it will result into summation of 0 to L integration of derivative of m square will be 2m. So 2m will come in, 2m will be there, 2 get cancelled, what remains m, and derivative of, since it's a partial derivative, we will have dou m upon dou x, the second component here. Now I want to maximize this value. So to test the condition of maximize or minimize value of ui, let us have the second derivative. We will try to minimize it, means again we have to derivate with reference to unknown force. That value deflection we have to minimize with reference to unknown force. So it will be second derivative of strain energy with reference to redundant force. So it will be dou ui upon dou x square. I am going to take second derivative. Summation of 0 to L ds upon ei is constant. U into v was the equation here. So m into dou 2 m upon dou x square, second derivative of the dou m upon dou x. In the second case, it will be dou m upon dou x square whole square. Okay, this will be the resultant with reference to what we say second derivative of minimization of the deflection caused by that force. Now if I separate the bending moment at any section, with this we can make a statement: the bending moment at any section is linear function of x. It's going to have linearity with reference to change in length. So dou m upon dou x is our constant, and dou 2m upon dou x square, the derivative of this constant will be 0, and we can say dou m upon dou x whole square, they are the positive values, and it says that hence of all infinite values of x satisfying the condition of equilibrium, the actual value of x is given by the value for which strain energy stored is minimum. That's a slight proof towards the second your Castigliano second theorem. Let's have one numerical for complete understanding about the concept. Numerical 1. A beam of a span L is fixed at one end and simply supported at the other end. It carries a uniformly distributed load of W kN per meter over the whole span. Find the reaction at the simply supported end by the principle of least work. Minimizing of the displacement is nothing but principle of least work. If I sketch up the things, and A is fixed and B is being supported by a reactive force, it is a prop cantilever subjected to UDL. If I put the bending moment at any section XX as shown in this section here, so we will have bending moment is equals to m equals to Rx minus W x square by 2. If I take strain energy concept in picture, we can write strain energy stored by the system will be 0 to L m square ds upon 2 ER. I am going to substitute the value of m here. It will be Rx minus W x square divided by 2 whole square into dx upon di. Now using the Castigliano concept, Castigliano second theorem, we can say derivative dou ui upon dou r. Dou r is nothing but the redundant force here under reference reactive force. So I am taking derivative of with reference to this. So we get result 0 to L 2 into Rx minus W x square by 2 the whole bracket multiplied by x into dx upon 2 EI equals to 0. So here 2 from the bracket goes downside, and the derivative of this particular bracket later on will be x. Now if I separate the terms inside the bracket, we can write r upon ei constant 0 to L x square dx minus W upon 2 ei in bracket 0 to L x cube into dx. If I take the integration of this one, it will be x cube by 3i. So it is written as r L cube upon 3 ei minus W L raised to 4 upon 8 ei equals to 0. If I take the terms on one side, like terms on one side, and rearrange the equation, is result into r equals to 3 by 8 WL. So with the minimization of your strain energy stored in a body, we can find out the maximum value of reactive forces which is being applied on the as a redundant force on the structure. So we'll go towards the concept of redundant trusses in upcoming lecture. Till then, be safe, stay at home, be safe, be healthy. Thank you.